Okay, let me get started here. So today's topic is missing data, um, and I guess this is a pervasive problem in research. So a lot of the concepts here are things you want to at least keep in mind when you do research. So see if I yeah, there we go. Okay, so. I'm going to talk first about just the missing value issues, and then we're going to talk about how you might be able to impute missing data. We'll look at what's known as single imputation, and then most of the time spent on multiple imputation for both continuous and categorical variables. And then we'll also talk about imputing missing outcome data rather than just covariate data. So in doing research, missing data is essentially inevitable. I don't know that in any study I've ever done where they've had complete data. And the issue is that missing data may affect the results of a statistical analysis. And most of the software that you do the analysis with is designed to do what we call a complete case analysis. In other words, it deletes missing values, whatever variables you're using in your analysis. It will eliminate or delete any observation that has missing values on any of the variables that you're looking interested in looking at. And if you have multivariable data or particularly repeated measures data, this missing data can be a really big problem. So we need to talk about why missing data is missing, or that is the mechanisms related to missing data. And so the concept of missing completely at random means that the missingness or the reason for missingness is not related to the outcome or to covariates. This is probably really rare to find data that's missing data is completely at random. Most of the time, data will be what we call missing at random. And what we mean by this is that missingness is not related to the outcome, but it might be related to the covariates. And then finally, not missing at random, or what we call non-ignorable missingness. That means that the missingness is related to the outcome. It can also be related to the covariates, but primarily this is the outcome, or that the missingness mechanism is related to the outcome. So let me give some examples here. So missing at random might be if it's, say, in the lab you have lab values that you want to analyze, and someone drops a test tube in the lab, that it wouldn't be related to the outcome that you're looking at. Say you were doing a weight loss intervention study and a research subject forgets about the appointment, then that would be missing at random. Or if in doing a survey question is overlooked, and then maybe a researcher forgets to record subject height and weight in a study, that would be considered missing at random, because you could assume that the missingness is not related to the outcome. Not missing at random, going back to the weight loss intervention example, if a research subject fails to show for the intervention because they think they haven't lost weight, then obviously that's not missing at random. The missingness is related to the outcome. or a survey question that's intentionally skipped. Common one might be income. It's not answered by the wealthy or the less wealthy. And sometimes race is not um, um, filled out or indicated because the person chooses not to do that. That might be related to the outcome. Then if you have particularly like repeated measures, say you have a quality of life questionnaire, um, especially if you're doing this over time, you measure, get a response to questions at baseline and say 3 months, 6 months, or a year. Typically, if this is quality of life, then as time goes on, the less well patients are not going to respond to it. And obviously, if a patient dies, they're not going to respond to it. So that's not missing at random. It's the response is related to the outcome of, say, for example, if you're doing survival or looking at patients' health over time. And then one that I use an example here that's actually more from the past. I'm not sure this is relevant today, but left ventricular ejection fraction used to be based on a physician's decision regarding to do the test if and taking into account the patient's health. And so in some cases, because this used to be done by injecting a medium into the patient if the patient wasn't healthy enough, that would be considered missing at random. But this could apply to any, say, test that was related to how healthy the patient was to get the test. So if that's the case, then the physician makes a decision and it's not missing at random. So when we do a complete case analysis, what we mean by that is we're going to use only the observations or the patients or subjects that have complete data on all the variables. And so obviously this is ignoring some data, the missing data. Now, it's possible that this is okay. And when it's okay, that you can get results if the cases, the remaining cases that have complete data are representative of the population. But it may not be representative. And so then your results might be biased. And then also when you exclude the missing data, you're obviously going to lose power because you're going to lose sample size. So I'm going to talk first about single imputation and what we mean by that and different ways of doing that. And as I'll end up with, this is usually a bad idea of a way of imputing data. So one common way that's been used in the past is to replace the missing data with the mean of the current data with the data that's not missing. Another single imputation method is to do what we call hot deck imputation. And essentially what this is, what you do is you find a matching case on some set of variables and replace the missing value with the data from the matching case. If you have a lot of variables, and it's very difficult to do. And then another common way that's actually more common is when you have repeated measures data, the method of last value carried forward. And I'll give some examples here, which also can be a really bad idea. So here's an example of some patients, and they have repeated measures data, baseline 1 month, 6 months, and 12 months. And so you can see that out of my 10 here, there's only 2 that have complete data over the time period. And so if we look at, say, a couple of these, say, patient number 2 is missing data at 1 month here. So as I mentioned, one of the things that we might do is replace this missing value with the mean. And what we're talking about here is the mean of all 1 month values, not the mean of all the observed values for patient 2. And then so this would be the case with others here. They're missing baseline, so you fill this in with the average of all baseline measures and so on. There's a couple here, say for example, patient number 3, where out of 12 months, they don't have any data. So to replace this value with the mean at 12 months is a little risky, because it's very possible here, if you have data like this, that this value here is not missing at random. And then the same with these others here. So if they have a valid value at one point and then for the rest of the time periods they don't, then you can't be sure that that's missing at random, and filling in with either the average or in this case the last value carried forward might really bias your results. So with the same data here, so let's say that we have some covariates in the data like age, sex, race, BMI, type 2 diabetes, and hypertension. And so if we do what I call hot deck imputation, then what we want to do is for each of these missing ones, we want to find another patient that has data for 1 month, but we're going to match on these variables. And so you can see it might be difficult to do this. And especially if you have continuous variables like age and BMI, then how are you going to match that? If you try to match it by an exact age, then you might not be able to find a value for it. So typically when people do this, they match on age, say within plus or 5 years, or maybe plus or minus 2 years. And then the same thing for the continuous variable of BMI. You could do this with, within plus or minus 5 kilograms per meter squared, or some other value that you think is reasonable here. And then the others like sex, race, whether they have type 2 diabetes, is a categorical variable. So you're going to have to, if you match on age and BMI, then find a similar patient that is the same age, same sex, same race, that whether they have diabetes, yes or no, or whether they have hypertension, yes or no. So you can see that it can get quite complicated to do this sort of imputation, but by and large, when we do these kinds of things, whether it's last value carried forward or hot deck imputation or replacing with the mean, we might very well bias the results of our analysis. So what we want to do then, if we have missing data, is we want to do what's called multiple imputation. And if you have a sample where the missing values are, say, less than 1% of your total sample size, then you just as well as drop those missing data from the analysis, because they're not going to make much difference. I mean, unless you only have, a few patients, but most of the time, if you, have more than, say, 30 to 50 or, hundreds or even thousands, and dropping the missing values is not going to really make that much difference. Sometimes you see people use less than 5%, but of course, 5% of 1,000 can be quite a few. So, but usually if the missing is very small, then you can just drop those from the analysis, do a complete case analysis. But if not, then as I mentioned, what we're going to do is we're going to impute the missing values to produce a data set. On the other hand, and then regarding the amount of missing, if you have a really large amount of missing, say in the range of 40 to 50% or more, then the imputation is at least in a lot of researchers' minds sort of questionable, because if you have half of the data is missing, it's like what are you going to be able to say about that? But anyway, those are just sort of guidelines, not hard and fast rules. So what do we do in multiple imputations? So what we do is we impute. In other words, we fill in the missing data, and we do that a number of times in order to generate a certain number of complete data sets. We'll talk about how many you need to do a little bit later. But what we do then is, once we have our complete data sets, we analyze each data set separately, and then we combine the results of each analysis. So if we have a, say, regression equation that we want to analyze, then we're going to do this however many times or however many data sets we have. So if we have 10 data sets that we've imputed, then we're going to do this analysis for each data set, in this case, 10 times. So in terms of the methods that are used for multiple imputation, in some way or another, we're going to use regression. In other words, we're going to model the dependent variable as a function of all the variables or the covariates in the data set. And as we'll see, then when we impute a data point, a data value, then in the next imputation, then that filled in variable could become a predictor of the missing values. Another method for continuous data, predictive mean matching, and this is actually sort of my preference if you have continuous data, to do predictive mean matching. But what it does is it generates a predicted value and then randomly selects the closest value from another patient in the data set that's not missing that particular variable. And the reason that this is preferred, I'll talk about in a minute, but predictive mean matching means that you're going to have predicted values that are within the range of your observed values. Markov chain Monte Carlo is essentially the same kind of thing, except that like just regression, it's going to draw values from some distribution, some known distribution, like the normal distribution. And then there's also a way of using propensity scores as an indicator variable for missing. We're not going to talk about that in this session, but that's another method that's used to account for missing values. So as I've gone over before, what we can do as far as imputing really depends on the missing data mechanism. And so if we have data covariates that are missing completely at random or missing at random, then we can impute data without in just sort of the regular regression or predictive mean matching methods. If our data is not missing at random, in other words, the missingness is related to the outcome, then we really can't do multiple imputation in the more common ways that we can do with missing at random. And I'll give some examples of that later on. So what we do is that typically, and this is kind of from the early days of multiple imputation, is that we generate 3 to 5 complete data sets. In a lot of cases, that's enough, but more recently, it's been shown that in some cases you need a lot more than 5 complete data sets, and I have a reference there on that. And there's been actually a fair amount of research that's shown that in some cases, depending on your pattern of missing and how much you're missing, how much data is missing, you need a lot more than 5 complete data sets. And so what we said, or then what we do is we mentioned before, we analyze each set individually. And so what we do then is we're going to combine the results. And as far as estimating the regression parameters, the betas of the regression model that we're looking at is just the average of all the betas over the M analyses, or however many analyses you've done. So if you've done 10 imputations, then it's going to be the average of all those beta coefficients divided by 10. If we want to, and we need to take into account variance in computing standard errors, then it's a little more complicated because we need to take into account both within variance of each data set and then the variance between the data sets. Because the procedure, the multiple imputation, introduces random variability because you have each data set that you generate is going to be different to some degree, maybe a lot different, or maybe not so much different than the one previous to that. And then, as I mentioned, how we combine results, and then that the number of imputations might vary from relatively small number to a large number. So assuming that the data is missing at random, then as I've indicated before, doing single imputation is not really optimal. In fact, most of the time it's a bad idea because you're going to bias your results. As mentioned, linear regression draws values from some known distribution like the normal distribution. And the problem with that is that you can get values that are outside your observed values. This is particularly true if you assume a normal distribution and say you have a variable or a covariate that has all positive values. If you draw from a normal distribution, you might get negative values, which are not possible in the real world. And as I mentioned, if you have continuous data like age or BMI or blood pressure, then predictive mean matching is really the preferred way because you'll always get a value within the range of the observed values. And then if we have binomial or categorical data, then we'll do logistic regression, and it'll make random draws from a binomial distribution or a uniform distribution, say between the minimum and maximum of your category values. So I want to give an example then from a data set that we have been working on for, well, actually, we just submitted the main paper a few weeks ago, but this is a study about hypertrophic cardiomyopathy. So it was included patients between the ages of 67 that had been diagnosed with HCM. And between 2014 and 2017, there were some 2,700 patients enrolled, although it turned out that some of these had to be dropped because they had no follow-up data or they actually weren't HCM patients. And there were 44 sites enrolling patients in 6 countries. And when we closed the follow-up study, we had an average of nearly 7 years of follow-up. The primary outcome, which we actually just submitted a paper on a few weeks ago, was sudden cardiac death. But a secondary outcome that was of interest, in which we published a paper on some years ago, was atrial fibrillation. And so that's the example that I want to look at. And as I have talked about before, in terms of multiple imputation, that what we did was to produce 5 complete data sets, sort of in a sequential fashion from least missing to most missing, as far as the particular variable was concerned. But then we also imputed missing values for 5 more data sets, where we just randomly assign them regardless of the amount of missing. And so we had a total of 10 complete data sets. I might also add that it didn't matter whether we did it sequentially or whether we did it at random. They essentially turned out the same. But so we had 10 complete data sets. And so, as I mentioned, the estimated regression coefficients, which was the outcome was the occurrence of atrial fibrillation, was just the sum of the coefficients divided by 10. That's really easy to calculate. However, in calculating the standard errors, as I mentioned, we have to take into account both the within variability of each data set and then the variability between data sets. And so I just given the formula for doing that. And so here's our data that we used as predictors of AF, atrial fibrillation. And you can see here that the missing data for the demographic variables and some clinical variables was quite small. Less than 1% or less than 2% in most cases. However, some of the variables that we looked at, the extent of missing data was a little bit larger. And in terms of the variables that were related to getting MRI of the data, you can see that the missing was a little bit more, but for any one particular variable, it was about 6% or less. Overall, the missing in terms of the number of patients was missing a rate of about 18% of patients. And so in the analysis that we did, which was lasting net, which is another session. But the analysis selected the most important variables. And so you can see the results here over the 10 data sets. That left atrial volume and contractile percent were always the first and second variables selected in all 10 data sets. And then there are others like BMI, you can see occurred quite often, but not always in the same sequence or in the same order. And so this is a table of the number of data sets that each variable the data sets in which it appeared. And so you can see that we have 11 variables here that appeared in all 10 imputed data sets. So our analysis then started out based on these 11 variables, and then we eliminated some by use of the log likelihood test. But you can see that the variables that you identify here might appear in more than one imputed data set, but the ones that appear in all 10 of them, or however many data sets you did, are probably the most, are obviously the most important ones that you want to look at. So in terms of the method that's used, a common one is what's called multiple imputation by chained equations, or MICE. And so this has basically 4 steps, or 5, but it begins by imputing, putting in a single imputation, such as the mean, for every missing value. And then the observed variables from the variable that you're imputing are regressed on all the other variables in the imputation imputation model. In other words, the particular variable becomes the dependent variable in a regression model, and all the other variables would be considered independent variables. Then when we get a imputed value for that missing value, it's then replaced with those predictions from the regression model. Then when we go to repeat the process in steps 2 to 4, then that imputed value becomes a value that we use in the imputation of the next variable that we're going to impute. I'll give you an example of that, since that's probably not all that clear. But so I'm going to use some data from the medicine clinic data, and this is just some of the variables, or some of the patients, I should say. And so you can see that it turns out for age, gender, race, and MSLV, we have complete data for those 4 variables. But for fasting glucose, random glucose, BMI, there's missing data. And for some of the other variables, like cholesterol, A1C, the HDL, LDL levels are missing data. But I believe that there was complete data for blood pressure, both systolic and diastolic. So we have a data set that has some missing values for variables that we are interested in as far as predicting our outcome. And so here's an example of the way that mice works. And this is from Stata, although this can be done in other packages as well. But so we have here are four complete variables. So we have no missing data. So we come to our fasting glucose. And so we're going to regress that on our four non-missing values, but we're also going to use the observed variables for others in the data set, cholesterol, BMI, blood pressure, and so on. So we're then going to impute a value for fasting glucose. So when it comes then to the value for random glucose, you can see that we're going to include the imputed values for fasting glucose. And then when we impute missing values for BMI, we're going to include the imputed values. They're no longer missing, so to speak, from both fasting and random glucose and so on. So we're using imputed values to impute other values. And so in the regression that we wanted to look at, we wanted to look at, this is just one example here of looking at A1C as a result, as a function of gender. And so we do 5 imputations, and we get the regression coefficient and all the other statistics related to that, the constant. Doing the complete case results, which in this data set I just took 9 with complete data, you see that we get somewhat different, although not much different, values for the regression coefficient. But of course, with the imputed data, we have much more power. So we can see that it still isn't significant at the 0.5 level, but it's in a sense more significant than the complete case analysis. And we get much narrower confidence intervals than we do with the complete case analysis. So what then if the data is not missing at random? Well, there's different ways that we can do this. I'm just going to give an example of one here of pattern mixture models. There's other ways of doing this, selection models, shared parameter models, and as I mentioned in the beginning, we can also use propensity scores. But here's data that again has observations at baseline 1 month, 3 months, up to 36 months. And so if we look at the data here, we can see that there's different patterns of missing data. And so, for example, the first one here has a missing baseline, and it's the patient is missing data at 24 and 36 months. Here's a patient that is missing data at 1 month and at 12 months, and so on. So what we mean by an intermittent pattern here is that if a value is missing, but you have data on either side of missing value, like say we'll take the second patient here. So I have a missing value at 1 month, but they have baseline and 3-month values. They have a missing value at 12 months, but they have data at 6 and 24 months and 36 months. So what we're going to do in pattern mixture analyses is we're going to assume that these are missing at random. So the missing data at 1 month here and 12 months here, and this one at 1 month and at 24 months, we'll assume, and the last one here missing at 6 months, we'll assume that they're missing at random, and so we can impute those just like we would normally do. However, for patients like the first one here and the last one, they have no values at the end of the observation period. So now we can't really assume, or it's not a good assumption to assume that these would be missing at random and we could impute these because these values at 24 months and 36 months for patient number 1 and patient number 4, we'd have to assume that those are not missing at random. So these could be patients that are either really got sick and we couldn't get any measure, or they actually died, and so they're not missing at random. But what we have then is a matrix where we would have patients with complete data from baseline to 36. Then we would have patients who are missing baseline, but they have all data out to 36 months. And then the next one would be missing baseline, missing 1 month, and complete data out to the 36 months. But for patients like these, their data would end at whatever their last observation was. So this one would be like 12 months. Well, and this one also 12 months, because we're not going to be able to impute the data at the end here, because we're assuming that's not missing at random. But we do have a matrix of imputed data out from the baseline to whatever is observed data or imputed data for these. And then we would have patients that would have complete data, whether it's imputed or observed, out to, say, 12 months here, and then they would not have data after that, and so on. And then we can analyze that that particular data set. So that's an example of pattern mixture models. I'm not going to take time to go into the other non-missing ways of imputing data. They actually get fairly complicated anyway. But I want to talk about imputing data from contingencies that are cell counts. And so I'm going to use just 2x2 tables here, since that's a lot easier. But in our 2x2 table here, we have cases and controls, and then in other words, cases are the ones who have the disease, controls or not. Exposures, whether they've been exposed to some treatment or some other factor, like race or gender, whatever. And then what I have here in the box is the way that you compute the chi-square. And any 2x2 table will have degrees of freedom equal to 1. That's how you get that or compute that. So for a 2x2 table then that's set up this way, what we're interested in is whether the cases and controls differ with respect to the particular exposure or the treatment that they may have had or not had. So we expand our 2x2 table here with cases where we don't know the outcome or we don't know the exposure. And so these are our cell counts and the row totals, then our column totals, and then the grand total is basically the sum of all the cell counts. But let's say that we have some outcomes that are missing for the exposures, and then we have some outcomes that are missing for those that have not been exposed. And then we can also have outcomes that are missing for um, those that have the experience the outcome and those that didn't experience the outcome. So I'm going to just take an example here that hopefully will be not too complicated to follow, but we're going to do this in a table, in a row by column table. We can do it for more than a 2 by 2 table, but obviously the computations get more involved. But the methods that we use are what are called likelihood methods, maximum likelihood or restricted maximum likelihood, or an expectation maximization algorithm. And so what maximum likelihood or likelihood function does is it's a distribution that's evaluated at the data, and basically we want to see how well does the function generate the observed data. And as I think I mentioned before, we can use the log likelihood test to see if there's a difference between the methods. So let me take a actual example here with numbers in them. And so we have aortic valve disease, and then what they've had radiotherapy, either yes or no, and there are cases that have the valve disease and the controls don't have the disease. And so what I've shown in this table is our complete data, but we have 70 other patients that we don't know whether they had radiotherapy or not for the disease, for the cases. 23 died and 47 are unknown. So in terms of the predictive values here, the positive predictive value, we would get, would be 9 out of 125 or 7.2. And I just put here the controls 1 out of 90, which is 1%. So how do we impute data in this case? Well, what we're going to do is we're going to use the data that we have to impute cells such that we have complete data. So we have 215 that have complete data, but we have 285 total patients that have some data. So here's our table that we had before set up. As I showed before, but so we have out here 70 patients that have valve disease, but we don't know their radiotherapy status, whether it was positive or negative. So if we compute the chi-square for just the observed data with the total of 215 here, we get a p-value of 0.03. But what we're going to do then is we're going to use our EM algorithm to include missing cases. So what we're going to do is revise the expected cell counts. So this is the program. You don't have to really pay attention to this. It'll be on the slides, but this is my algorithm in, originally wrote this in S+, but it'd be the same thing in R. And so my function includes what I have here are the 4 cell counts. In this case, the numbers for the ones that were missing, the rows missing, and then this would be for if there are any missing, not outcomes, but this is the B here is the missing outcomes. The C would be the missing therapies, or in our case, the radiotherapy. And so I set initial values here, And so then what I'm going to run is the algorithm, which looks like this, but you're basically just using cell counts to the observed data to impute the missing cell counts, the missing cell values. And then my last statement here, if I get a first, the very last one that I computed, is it any different from the one before that? And if it's less than 10 to the minus 10 in this case, then I stop. And so here's the end where I get the predicted cell counts. And this is just a loop that goes back to the beginning of the program and loops back through till we come to the end of it, or get a value, a difference in log likelihoods that's less than 10 to the minus 10. And so this is what it looks like on output, a value for each cell. My starting ones where I said that the proportion in each cell was the same. And then I come out with a table that looks like this, where I then compute my or fill in my missing cells, or the missing data from the cells. So I come up now with 14 cases that had radiotherapy, 181 that didn't. Now I get a different total here, so I have a complete, I've used all the data here, and these are the values that I now get, which, if you remember, are very close to the observed values, and the chi-square has about the same p-value of 0.03. So using that method, the expectation maximization, I get essentially the same thing that I did with using just the observed data. Then I can do restricted maximum likelihood. Well, would have the same thing, but the parts of the program that I had for the EM algorithm, but this is the loop, and where I go through and or update the row plus column expectations. And that's would be my output. Come to the end of that, and here's my final tally, where now you see that I get a very different result than I did with either the observed counts or the EM counts. So now I have all my observations, my 285 observations, but now I percents here, like the cases, this would be my positive predictive value, is 4.6, whereas before it was like 7 something, and now there's no statistically significant difference. So I get very different results depending on the different procedures that or methods that I use. So then we can compare these. As I mentioned before, we can take 2 times the difference in log likelihoods. I do that between my the maximum likelihood and the restricted maximum likelihood, and I get a chi-square that shows that they're different. And is one model better than the other? Well, statistically speaking, we have difference in the model, so it may be difficult to make a decision. So here's the different counts that results that I get with. Here's the observed table. Here's the maximum likelihood table, and here's the restricted maximum likelihood table. And it turns out that these two basically give different results. Now, in doing this, if controls as well as cases were missing the radiotherapy status, I just had the cases, then the two methods would probably result in the same thing. But if they do differ, then you're going to, as I have shown, that you're going to get potentially different results. Which one you take, the restricted maximum likelihood is preferred, but not by everybody. So one other example that I was going to go through is screening for diabetes. I won't take time to do that because I'm running out of time and I want to take some time, but we did the sort of the same thing and calculated the sensitivity and specificity, and then I showed the difference in the maximum likelihood and the restricted maximum likelihood. Here, there's no difference. And then the diagnostic statistics, you can see that they're fairly similar, except for the positive predictive value that it's actually quite a bit lower for the maximum likelihood and the restricted maximum likelihood, which you would then take these as being more accurate than the complete case analysis. Then missing events, I won't take time to go over that. Let me see here. Let me go to my comments. One thing I want to leave you with is that you can never be 100% certain that the data are missing at random or not missing at random. But when you do multiple imputation, you need to specify your assumptions. And then if the study is a comparative effectiveness study, that is, if you have a treatment group and a control group, then you can't use the study group for an imputation variable. In other words, you can't use that in imputing the missing covariate values. And then the other last two, I've mentioned those before. So the software, it's quite extensive, missing values in both SAS, in R, and actually in SPSS has a nice package for doing that. And then there's a package called Solus Statistical Solutions that has a missing data library. And then these are a number of references. Some of them are sort of the classics in missing data and analyzing missing data. Then the last one is the more recent one where you can calculate how many imputations you need, although that's also has its issues because it's circular in the sense that you have to run the program first or run your analysis first, and then based on those results, you can sort of figure out how many, or you have to choose a number of imputations to begin with, and then using that, you calculate how many more you might need or how many less you might need. So I'll end there as I'm really out of time and leave time for any questions if you have any. So I think there's a not the chat, but I think there's another thing for questions if you have any, or if you don't. And as I say, we're kind of out of time here. If you have any questions or that you think of any questions later on, feel free to email me those questions and we can discuss it online. Also, I will, in fact, I'll remember to do that as soon as I'm done here, is I'll send these internets to the folks at Georgetown, and they will make them available to you as well as the recording on YouTube. So again, thank you for your time and attention, and we'll meet again next week.